flavors of PGA.
Yep. There's so many flavors of everything nowadays.
True enough.
Okay, so digital ICs. There's a bunch of families. There's probably even more than this, but the typical ones um, of fairly modern of TTL. There was RTL before that. It was, I
DTL.
guess, when I first started, there was RTL. Uh, Then along
DTL.
came CMOS, where they were able to reduce power, run at a lower voltage, and get the same, pretty much the same kind of speeds, unless you were doing um, some of the high speed TTL. Uh, what was the ECL, emitter coupled logic, was really high speed, but really high power. And then the Schottky, low power Schottky. And then along came BiCMOS. I was kind of retired by that time. I don't ever remember BiCMOS. And then we have gates, which are your typical AND, NAND, OR, NOR, exclusive OR, uh, kind of the typical ones you're going to find. And all these other things are built up out of these gates to make flip-flops and shift registers and stuff. And then you have PLDs, or programmable logic devices, or field programmable gate arrays is another name for those. In some cases, you can program it in the field and change it. In some cases, it gets programmed at the factory and you don't change it. A lot of the modern SDR radios make use of uh, those programmable gate arrays to do a lot of the processing, where it's pretty much fixed. So what is a digital integrated circuit? It's usually a bunch of logic gates uh, connected together on a single piece of semiconductor material or substrate and put in some kind of plastic package, or I guess they still do them in ceramic for military type stuff. Used to see ceramic packages. I haven't seen them in a long time. TTL stands for transistor logic. It's just the way the gates were built. They're fairly high speed, high power consumption relative to CMOS. And CMOS is complementary metal oxide semiconductors. So they're using MOSFETs to build these, which is how they get the high input impedance, the low output impedance, and low power. CMOS, one of the differences is TTL uh, switches, if you're running it at 5 volts, it may switch between a logic 0 and 1, somewhere below 2 volts, volt and a half in that range. Where in CMOS, it switches at half of the power supply. So 5 volt CMOS is going to switch approximately 2.5 volts. So you get a little better noise immunity. Let's see. We talked TTL, CMOS. They probably became a lot more common use than TTL. I guess TTL is still around. Um, and there's BiCMOS, which is a combination. So you can have a high input impedance device with a much lower output impedance. TTL devices could supply more current than a CMOS device. And as I recall, the fan out was what, 10 for TTL? At like 1.5 milliamps per, something like that. That's going back a long time.
Oh,
A TTL NAND gate is typically constructed like this, and it gives you an inversion. To make an AND gate, whether it's CMOS or TTL, you have to add more transistors to invert it. So an AND or an OR is actually more complicated than a NAND or a NOR. And that's why most things are built out of NANDs and NORs. And you can use De Morgan's theorem to go back and forth between all those good things. You don't have to learn De Morgan's theorem. What of the following is an advantage of CMOS compared to TTL?
Alpha.
I think it's alpha. Which of the following digital logic families has the lowest power consumption? Yeah. Yeah, regular Schottky TTL was not low power. Low power Schottky was down close to CMOS, if I recall. And fast. Why do CMOS digital integrated circuits have high immunity to noise on the input signal or power supply? Charlie. Which of the following is an advantage of BiCMOS logic? Charlie. It's a hybrid. Okay. We can also have tri-state logic, where instead of a 1, it can be a true or false, or a 1 or 0, or a high or a low. You can put it in a high impedance state. You normally do that if you want to create a bus and have multiple devices on the bus. So you have an enable signal on the device. So if it's not enabled, it's in a high impedance state, so it doesn't affect the loading or impedance on the bus. It's probably all you need to know. The truth table, for one, you see it's got this extra enable pin. So because it's got a circle, it means it's inverted. So it takes a low to enable it. So if we look at the truth table, and this would be a regular NAND gate, when the enable is low, okay, it's going to act like a NAND gate. When the enable is high, the output is just going to be whatever, it's going to float.
Is that how they're depleting the tri-state device?
Say that again?
Is that how they are depleting a tri-state device with that inverted enable?
Yeah, they're typically that way, although there's no reason why it couldn't have been a positive enable.
But it would be a tri-state.
But I think one of the practical reasons for having that is if you don't want to use it in the tri-state mode, you just ground that pin. And it's always enabled. Because sometimes you use devices other than the way they originally intended them. So what is tri-state logic? Alpha. Okay, so we have different symbols. Okay, so 1 is a standard AND gate. 2 is a NAND gate, which is an inverted AND, or not AND, which is where NAND comes from. 3 is an OR gate. 4 is a NOR gate, or inverted OR. Then we have a standard inverter. And the little circles represent inversion. So whether it's an input or an output, that means it's inverted. And then we have this number 6 over there, which is not a logic gate. Huh?
That's a rocket ship.
It could be some kind of analog circuit, maybe. I don't know.
It's a hip logic.
I think it's a comparator. Op amps typically had a square face.
Yeah, it looks a little like a comparator, but I don't think it is. Okay, so in 6.3, what's the symbol for a NAND gate?
2,
What's the symbol for a NOR gate?
4,
What's the symbol for a NOT or an inverter?
5.
Okay. When you're using digital ICs, you may not use all the pins. I mean, you get a package that's got 8 inverters in it, which is a typical one, 7408, I think. If you don't use all of them, you don't want them floating around with noise and turning on and off, because that affects power and generates noise in the circuit. So you use pull up or pull down resistors to essentially, you could either tie the input high or tie it low, it doesn't really matter. Okay, so that it doesn't change. If it was TTL, you'd probably pull it high, because that way it's not going to draw any current. Well, less current. So normally, if it's using a pull down, you connect to ground. If you're using a pull up, you normally connect it through a 1 or 10K resistor or something like that. You don't normally do a direct connection to VCC. So what best describes a pull up or pull down resistor? I believe it's Bravo. Okay, comparators. It's an IC that's kind of analog and digital. So it looks at an input voltage and compares it to a reference voltage, and it changes the output from true to false or false to true, depending on whether that input voltage is greater or less than the reference voltage. And that's the basis for doing analog digital converters. They'll use those comparators. One of the things that they put in a comparator is a hysteresis circuit, so that if you exceed the threshold voltage and turn it on, and there's a little bit of noise, and it drops below that threshold voltage, instead of it turning off, the hysteresis circuit requires that it drops a certain amount below the threshold voltage before it'll switch back to off or 0. So the hysteresis circuit is there to avoid noise on the input signal. But then I think a little bit later, we'll find out how we actually inject noise to get a half of an LSB out of the thing, which still I have trouble wrapping my mind around, but it works. Double bounce again. Come on. There's a typical circuit. In this case, it's got a flat front instead of a curved one. And we have the 2 inputs, the input and the reference, your power, and then an output, which is either high or low, depending on whether the input is above or below the reference voltage. So what happens when the level of a comparator's input signal crosses the threshold? What's the function of hysteresis in a comparator? Okay, programmable logic. These are a collection of gates that have multiple connection points that you can program and configure it in kind of any way you want. So it's a little bit of a sandbox, sort of. It may have millions of logic gates, and you wind up, for the very complicated ones, have to use some design language to actually, generate the code to program the things. They call that the hardware description language. And I think each one of the manufacturers that does these things has their own proprietary set of tools. Here's a typical circuit of a very simple one where you've got two inputs that coming into an inverted, non-inverted output. And it goes to these, splits off to all these fuses. Okay, so in this case, you would blow the fuse on the ones you don't want connected and just leave it connected where you want. So that would allow you to connect those inputs to any of the inputs on those other gates. And that's kind of the way the whole thing works. But, imagine it with thousands of these things. So what is used to design the configuration of a field programmable gate array?
B.
A hardware description language that goes by various names depending on whose it is. That was it.
There's no table.
Yeah, I got tired.